In this demonstration, you will learn how to use the steady flamelet model to describe the reacting flow through a can combustor. I am interested in comparing the results generated by the steady flamelet model to those prepared using the eddy dissipation model. I have started this demonstration with Fluent set to run a diffusion-controlled reacting flow analysis on this can combustor. Currently, the combustion reaction is described by the eddy dissipation model. To access the steady diffusion flamelet model settings, I must change the species model from species transport to non-premixed combustion. In non-premixed combustion, fuel and oxidizer enter the reaction zone in distinct streams. This is in contrast to premixed models, in which reactions are mixed at the molecular level before burning. State relation describes the thermodynamic state of the species in the flame. If the equilibrium option is selected, reactants and products are considered to be in a state of dynamic equilibrium, and the detailed kinetics of the reaction mechanism are not required. In contrast, the steady diffusion flamelet model uses detailed chemical kinetics to describe the combustion reaction. Flamelet structures may be imported from an external file or can be generated in Fluent. I will create a flamelet, but first I must specify the kinetics of the combustion reaction with a chemkin file. In this case, I will use a built-in reaction data file which describes the combustion of methane. When I import the kinetic data, options describing the fuel and oxidizer composition, as well as the flamelet and probability density function, become available. It's best to go through these tabs from left to right. In the Boundary tab, I specify the composition and the temperature of the fuel and oxidizer streams entering the reactor. In this case, the fuel will be methane, so I will give it a mass fraction of 1. The oxidizer is air, which is roughly 23% oxygen and 77% nitrogen by mass. Notice that I can set the temperature of each fluid in this menu. Flamelet controls can be used to change how the flamelet is numerically described. These settings are rather advanced, so I will keep the defaults. In the Flamelet tab, I can control the size, maximum number of flamelets, and the scalar dissipation of each flamelet. Once I am satisfied with my flamelet definition, I generate the flamelet file. This can be saved, modified, and used in different simulations. With my flamelet generated, I can now create a probability density function, or PDF, that describes the variable values as a function of the Schwab-Zeldovich variable, denoted as the mean mixture fraction, which depends on the relative amounts of fuel and oxidizer in a given volume. When the mean mixture fraction has a value of 1, the fluid is composed entirely of fuel. Conversely, when the mean mixture fraction equals 0, the fluid is composed of pure oxidizer. By default, the PDF is described by a beta function, which can be visualized in 2 or 3 dimensions for each variable. This is the PDF for the mean temperature variable. The y-axis describes the scaled variance, the x-axis describes the mean mixture fraction, and the z-axis describes the mean temperature of the reacting fluid. As we can see, the temperature of the fluid increases as the fraction of fuel decreases due to combustion, reaching a maximum at a certain composition of fuel and oxidizer. The generated PDF will act as a lookup table in the final calculation. At this point, the steady flamelet model is fully defined and the chemistry of the combustion reaction has been pre-processed. All I need to do is define the fuel inlet by giving it a mixture fraction value of 1 and set some solver controls. As with most reacting flow problems, the equations describing mixture transport and energy changes caused by reactions tend to evolve a bit slower, so it's best to solve these equations using an inflated timescale factor. I can now submit my case to the solver. In preparation for this portion of the demonstration, I prepared a few plots. Here's a plot showing how the mean mixture fraction changes as the fluid traverses the canister. Here's the CO2 mass fraction contour plot at the XZ plane. I can compare this plot to the plot produced using the eddy dissipation model at the same location. As we can see, the flamelet model predicts a significantly different CO2 mass fraction contour. Despite the differences in each model, both models predict similar mass-weighted average mass fractions of CO2 exiting the combustor outlet during the steady state. However, the flamelet model predicts less CO2 exiting the combustor and, due to its more realistic description of combustion kinetics, is considered to be more accurate. This concludes this demonstration, showing you how to solve a non-premixed reacting flow problem using the steady diffusion flamelet combustion model.